Hello, Calc, and welcome to your first online lesson. So we're going to go ahead and do 6.3, volume of solids with known cross sections. So we will be using some more integrals again, like we did with rotational volumes. So if you printed off the notes that were posted online, I just gave you the graphs. I didn't give you any three-dimensional looking pictures. So here in this presentation, you will see what should be what the three-dimensional figure would kind of look like. You can see a few cross sections there in this picture. So you can see here, this is your graph of y equals 2 sine x from 0 to pi over there. And then your cross sections, what it means is those cross sections are really popping out at you up out of the xy plane. So this is what it would kind of look like. So the base is bounded by some sort of region that's given to you. Your cross sections are perpendicular to the x-axis and are semicircles. So if you have semicircles, the diameter is in the plane, and then the semicircles are popping up out of the paper. So what this would look like is what you would want to do is find the area of a specific cross section and then add infinitely many of those together, which would be represented by an integral. So first, it's helpful to remember what the area of a semicircle is. The area of a semicircle is 1/2 pi r squared, just half of a circle. Then it's helpful to know what your diameter is, and then use that to find your radius. So our diameter is going to be the base of each circle, semicircle, which basically goes from the x-axis here up to our function. So our diameter is just going to be 2 sine x. So then your radius is going to be half of that. So your radius is just 1 sine x, or just sine x. So then our area is going to be 1/2 pi times the radius squared times sine squared. All right, so then that's the area of one semicircle. So the area or the volume of infinitely many of those added together is going to be the integral from 0 over to pi there, because we're adding the semicircles just between there, of 1/2 pi times sine squared dx. And most often you'll see that we pull out the pi term as a constant. So 1/2 pi times the integral from 0 to pi of sine squared of x dx. And this would be an example of an integral that you could evaluate using your calculators. We can also have cross sections that are squares. So our next example here shows the graph. It's not drawn in super well, but the graph of 2 to the negative x, and the cross sections coming up out at you are squares here, with one of the bases in that xy plane there. Okay. So to get the area of a square is just the base times the base, so the base squared. So what we're going to need to figure out of these squares is, what is your base going to be equal to? So what is the length of each of these bases in the plane? So each of these bases just goes from the x-axis up to the function 2 to the negative x. So your base is just 2 to the negative x, which would mean then your area is 2 to the negative x squared, which, power to a power, you just multiply the powers. So this is 2 to the negative 2x. This would represent the area of one of your cross sections. To get infinitely many of them would give us the volume, and that would be the integral. We're going from 0 to 4 of 2 to the negative 2x dx. So that would be the volume of that solid created with those particular cross sections. And again, this would be something you could evaluate on your calculator. All right, just a different function with the base now bounded by 15 minus x. So if you look at the picture, you can see here, it's just a straight line, 15 minus x. We have the diameters of each semicircle in the plane there, and then the semicircles are popping up out of the paper. Okay, so first we need to do the area of one semicircle, which is half of pi r squared. The diameter of each of our semicircles goes from the x-axis up to the function, so it's just 15 minus x. So then your radius is going to be half of that, so half of 15 minus x. So the area is going to be 1/2 of pi times the radius, 1/2 15 minus x, all squared. So this, you just have to be careful when you're plugging your radius in, make sure you square the whole radius. Sometimes people will be tempted to only square the 15 minus x. So the area of one cross section is going to be 1/2 pi times, when you square a product, 1/2 times 15 minus x, you square each part of that product. So it's going to be 1/4 15 minus x squared. Okay, so I squared 1/2 and I squared 15 minus x. Simplify the area of that cross section just a little further. 1/4 times 1/2 is 1/8, so you'll get 1/8 pi 15 minus x squared. So that's the area of just one cross section. To get infinitely many of those, we would get the volume, which would then be the integral. Now we're going from 0 to 15, and this is because the x-intercept of that graph happens to be 15. You might have to use some algebra in some problems, or just make sure you accurately draw your graph. So 0 to 15 of 1/8 pi times 15 minus x squared dx. And if you wanted to simplify that a little bit more, you could pull out the 1/8 pi as a constant. 1/8 pi integral from 0 to 15 of 15 minus x quantity squared dx. And then this integral you could plug into your calculator. All right, so we've seen some pictures now that have given us what the solid will potentially look like, but on test quizzes, stuff like that, you won't have that luxury. So let's see a couple of examples here and see if you can figure out what the representative cross section would be, and then see if you can set up the integral. So pause here for a minute. See if you can figure out what your area of one cross section would be, and then try and apply that to an integral. All right, so if you look at this screen, you can see I have, if I highlight kind of what I did as I went here, I figured out what the area of a semicircle would be, 1/2 pi r squared. We have the diameter and then what the radius would be. So if I put that radius into the area formula, you would see 1/2 x squared plus 1 squared as your radius. Simplify that. The area of one cross section is going to be 1/8 pi x squared plus 1 squared. Then put that into a volume formula, and you can see that your volume is represented by this particular integral. This is me trying to highlight it. Let's see if you can try the same thing with this particular example. All right, as you can see, our cross sections are squares, so the base is over here in the plane, and then the squares are popping up out of the paper at you, or out of the screen, I guess in this case. So area of one square would be base squared. Your base is going to be from the x-axis to the function, so square root of 9 minus x squared. So then you do the base squared, and you should just end up with the area of a cross section being 9 minus x squared. Then to find the volume, we put that into an integral. We are layering those from 0 to 3 of 9 minus x squared dx. So that should pretty much take care of just the examples of semicircles and squares for cross sections. You may notice on your worksheets that we have other cross sections that pop up. Again, you can always drop in on that Google Hangout, text me on Remind, or send me an email or a message on Schoology. I can certainly help you with any of those problems. Don't forget to check out Schoology, the 6.3 LT check that's posted there. That will be part of your grade and will be used for daily attendance. Thanks. See you guys tomorrow.